Okay, so we're going to look at how to solve this collision problem. It says a 2 kilogram cart moving at 3 meters per second hits a 1 kilogram cart at rest. They stick together. So we've got a couple of clues of what kind of problem this is going to be. One is, says they stick together. That tells us that it's going to be an inelastic collision. The other thing, quite possibly more obvious, is that the title says inelastic collision. So we're going to use those types of equations. So when we're solving collision problems, we always use conservation of momentum, meaning that the momentum, the initial momentum, is going to be equal to the final momentum. We're going to use more specifically the equation here for inelastic collisions. So we have, this is what our initial momentum looks like when we break it up into the masses and velocities. And then here's our final momentum, which is going to be the final velocity times the combined masses because they stick together. So let's look at what our specific numbers and things are going to be for this equation. So we can, I like to just take the numbers from the story problem and transfer them into what I know as variables. So we can just kind of go number by number and figure out what those things are. So we have, first we have 2 kilograms. So we're going to call that mass 1, moving at 3 meters per second. Cool. So that's going to be our initial velocity 1. V1 initial is 3 meters per second. It hits a 1 kilogram cart at rest. So mass 2. So in our story problem, we have these 3 things that are given as actual numbers. And then there's one sneaky one that's not so much given as a number, but there's a number hidden in there. And that's this at rest. So that tells us the initial velocity of the second cart, which is just going to be 0. We've got V2I equals 0. Now to find, the problem doesn't actually say, but what we're going to be finding here is the final velocity. Okay, find VF. All right, our equations, I think in this case, I've got them right here. That's pretty nice. So that'll be just fine. We can draw it. That helps us visualize what's happening. I'm going to kind of draw this as the initial and then the final. And I'm going to use 2 different colors for that. You don't have to get this as fancy with your own drawings. You don't have to draw anything at all. You just do whatever it takes for you to be able to kind of visualize and understand the problem a little bit better. But I'll just use black for initial. Got one cart that weighs 2 kilograms. Another cart, make it a little bit smaller, weighs 1 kilogram. This one, not moving at all. Velocity equals 0. V equals 3 meters per second. That way. All right, so this is before the collision. And then after the collision, we've got carts now kind of stuck together as one big cart. Still have the same masses. Now they are moving with some unknown velocity, V final. So this is what we're looking for and trying to find. All right, so we're going to be using this equation of M1V1I plus M2V2I equals the combined masses M1 plus M2 times the combined final velocity VF. Now we can just start plugging in numbers because we already wrote what those are. We can just plug them in. So we got 2 times V1I is 3 plus 1 0 equals 2 plus 1 times VF. We'll just do all this math. So it's going to be 6. That's going to be 0. That'll be 3. We've got 6 equals 3 VF. Divide both sides by 3. And then we get that VF equals 2 meters per second. Ta-da! It's that easy. Okay, so we just did this cart collision problem when it was an inelastic cart collision. Now we're going to do a very similar one. It's just going to be now an elastic cart collision, where instead of the carts sticking together and moving kind of as one new big mass, they bounce apart. So now instead of using the this equation for inelastic collisions, we're going to use our 2 equations for elastic collisions. And start over here. So I'm going to draw what the new situation is. So the initial situation is still the same. We've still got big cart, smaller cart. Yeah, we still have those same initial conditions. But now, after they hit, they're not stacked together, so we don't have one combined velocity. We've got a V1F and a V2. We know that after they hit, this one's obviously going to be going direction. We actually don't even know the direction that this one's going, because it could be that they hit and then it bounces off and goes the other way, or it could be that it hits and continues going in the same direction, but not quite as fast as before, because some of that got transferred to the other cart. So we're going to figure those things out. So our knowns are actually going to be exactly the same as last time. We've got M1 equals 2 kilograms. Put this down, just copy the other one. V1I equals 3 per second equals 1 kilogram. V2I, cart's still starting at rest. That's still just 0. Now, because there are 2 final velocities, we need to find those 2 things. So we're finding V1F and V2. We're going to use both of these equations because we have 2 variables that we're trying to find that we don't know. So we're going to need 2 equations to find. All right, now we go ahead and just plug things in again. M1 V1I plus 2 1 V1F. That's a lot to write, huh? Plus M2VF. All right, now we start plugging stuff in. 2 is 3 plus 1 0 equals 2 times V1F plus 1 is V2. So we'll end up with 6 equals 2 V1F plus 2. That's as far as we can get with just this one equation alone. Now, we can, over on this side, we're going to work with the other equation. So we've got V1I plus, oh, I wrote that wrong. I need to fix that. V plus V2I. Oh, wait, no, I didn't write that wrong. That's right. It's the 2 V1s equal the 2 V2s. I remember stuff. V2I plus 2F. All right, now we just plug stuff in again. We got 3 plus F equals 0 plus V2F. All right, now we're going to have to find a way to combine these 2 equations. I think our easiest way is that since both of these variables, the V2F in both cases, they have the same coefficient of 1, we can rearrange these equations to get V2F by itself, and then we can use that to combine them. So I'm just going to rewrite this as V2F equals 6 minus 2V1F, because we're moving it to the other side. V1F. Similar thing here. So we'll have, well, it's already on its own here, so that's awesome. So we've got, I'll just rewrite it though still. 2F equals 3 plus V1. Now, I'll just substitute this in for V2F here. We'll have our combined equation. So we've got 3 plus F equals 6 minus minus 2 V1F. So we can subtract 3 on both sides, 3 outside, and then I'm actually also going to add 2 V1F both sides. And then we'll end up, that cancels, just end up with 3F equals 3. So you can probably figure out pretty quickly, we'll divide both sides by 3, and we'll get V1F equals 1, add a unit, meters per second. Box around that, that's half of our answer. That's one of the things we were looking for. Now we just need to plug this back in to get V2F. We could plug it into either one of these equations, it will work just fine, but this one's slightly simpler, so I'm going to use this one. So we've got V2F equals 3 plus V1F, which we just found, is 1. V2F equals 4. Now, we just look at our answers and compare them back to like our drawing situation and see if that makes sense. So, we've got a big cart going 3 meters per second. It hits a little cart. After that, the big cart still is going forward, but not nearly as fast. It went down from 3 meters per second to 1 meters per second. Makes sense. It hit something. The little cart is going forward, it's actually going faster than the big cart was going initially. But yeah, that can make sense too, because well, it's smaller than the cart that hit it, and we know that momentum was transferred. And since momentum is mass times velocity, a bigger mass with smaller velocity transfers some of its momentum to the smaller mass, so it makes sense that it could very well have a bigger velocity. So yeah, I think I'm good with these numbers. They make sense.